When you search for something, you start with what is closest. If you lose your keys, you check your pockets first. If you want to explore new territory, you begin with your own backyard. This is common sense. This is logic. So when astronomers decided to search for planets beyond our solar system, they turned their attention to Alpha Centauri. Not because it was special in any unusual way, but because it was near, 4.37 light-years away. In a universe measured in millions and billions of light-years, this distance is almost nothing. To understand just how close that is, consider this. Light from Alpha Centauri that reaches your eyes tonight left that star in early 2021. When you look at most stars, you are seeing them as they were hundreds or thousands of years ago. When you look at Alpha Centauri, you are seeing it as it was during the pandemic. That is how close it is. And it is not just close, it is bright. Alpha Centauri is the third brightest star in the night sky. If you live in the southern hemisphere, you can walk outside on any clear night and see it shining there, steady and unmistakable. For astronomers, this combination of proximity and brightness made it the perfect target, close enough to study in detail, bright enough to see clearly. They began searching in the 1950s. Decades passed. New telescopes were built. New techniques were developed. Technology that once seemed impossible became routine. We found planets around stars 10 times farther away, 100 times farther. Thousands of planets orbiting distant suns. Some of them small and rocky, others massive and strange. But around Alpha Centauri A and Alpha Centauri B, the two main stars of the system, we found nothing. No confirmed planets, no clear signals, just noise and uncertainty. This absence was not just puzzling, it was frustrating. Because if Alpha Centauri has planets, it changes everything. It means our nearest stellar neighbour could have worlds we might one day visit. Not in some distant hypothetical future, but within the scope of realistic human ambition. Probes travelling at a fraction of light speed could reach Alpha Centauri within a human lifetime. It is the only star system where that statement is true. But there was a deeper reason the search mattered. If planets exist at Alpha Centauri, then the galaxy is full of them. Planets around every star, worlds beyond counting. But if our closest neighbour has none, then maybe planets are rare. Maybe the universe is emptier than we hoped. So astronomers kept looking. Because this should have been easy. The closest sun-like star, the brightest target. Every advantage on our side. It should have been the first place we found planets, not the last. But it was not easy. It was the hardest target they had ever faced. And the reason why would force them to confront a paradox they had never considered. There is something quietly profound in the idea that nearness does not guarantee clarity. We assume that what is close should be easy to understand, that proximity equals simplicity. But Alpha Centauri taught a different lesson entirely. The very qualities that made it seem like the perfect target, its brightness, its closeness, its steadiness in our sky, were exactly what made it impossible to study in the ways astronomers had learned to trust. Sometimes being close is exactly what makes something impossible to see. For 70 years, this star system held its secrets, not because it was hiding them deliberately, but because the tools we had were designed for different kinds of problems. We built telescopes to find faint, distant objects. We developed techniques to tease signals from the edge of visibility. And then we turned those instruments toward the brightest, nearest star within reach, and discovered that all our clever methods failed. The moth beside the floodlight. The coin dropped in bright sunlight. Real, present, but invisible, because the light overwhelms everything. And so this search continued. Patient, persistent, waiting for someone to ask a different kind of question. Not how to look harder, but how to look differently. Not how to build a bigger telescope, but how to teach an existing one to see what it was never designed to see. The story of Alpha Centauri is not really about a star. It is about the limits of seeing, and what happens when we push gently but insistently against those limits, until something finally gives. If you feel your thoughts beginning to wander now, that is perfectly fine. The stars have been there for billions of years. They are patient, and the story of how we learn to see them, well, that story unfolds slowly, the way all good mysteries should. At first, Alpha Centauri seemed like the perfect testing ground, the closest sun-like system, the brightest nearby beacon in our sky. If planets were anywhere, Surely they would reveal themselves here first. Yet the closer astronomers looked, the more this star system turned into a trap. Alpha Centauri A is the third brightest star in the night sky. That sounds impressive, but for planet hunters, it is a disaster. Finding a planet next to such a star is like trying to spot a moth flying beside a stadium floodlight. The moth is real, it has structure and motion, but your eyes are overwhelmed. The detector does not fail because it is weak. It fails because it is too sensitive. When light pours in with that kind of intensity, every instrument built to capture faint signals simply drowns in brightness. The planet you're searching for might be right there, glowing softly with its own reflected light or its own gentle heat, but the star beside it is shouting so loudly that nothing else can be heard. Then comes the second twist. Alpha Centauri is not one star but two. Alpha Centauri A and Alpha Centauri B orbit a shared centre of mass in a slow 80-year dance. When you point a telescope at one, the other leaks into the image. Their light overlaps, their signals interfere. Coronagraphs, those clever devices designed to block out a star's glare, can manage one bright point, but not two at once. It is like trying to hold up your hand to block the sun, only to have a second sun slide in from the side. No matter where you position your hand, light finds a way through, and somewhere farther out, Proxima Centauri pulls softly at the entire system. A small red dwarf, faint but gravitationally real. Any planet near Alpha Centauri A or B must live in a 3-star environment, with orbits constantly nudged and perturbed. Stability becomes a question, not a guarantee. Planets, if they exist here, are not floating in the simple, predictable paths we find in calmer systems. They are dancing to a rhythm set by 3 partners, and predicting where they will be at any given moment becomes vastly more complicated. On top of this, Alpha Centauri is racing across the sky. Its proper motion is high, so its coordinates slowly drift against the Milky Way background. Telescopes must be retuned, calculations updated, software rewritten. Miss by a tiny angle, and the star slips off the instrument entirely. What you thought you were observing turns out to be empty space, or worse, a completely different star masquerading as your target. And behind it all lies a crowded starfield, thousands of distant suns sprinkled across the same patch of sky. Every faint dot could be a nearby planet, or it could be a star hundreds of light years behind Alpha Centauri, simply passing through the same line of sight. Only years of patient tracking can reveal which ones move with Alpha Centauri, and which only pretend to belong. The background becomes a puzzle unto itself, filled with imposters and false signals, each one requiring careful elimination before the real signal, if it exists, can emerge. Proximity, brightness, motion and complexity all fuse into a single problem. The nearest star system did not just refuse to help, it turned itself into a test that ordinary tools could not pass. Every advantage became a disadvantage. Closeness meant brightness, brightness meant blindness. The double star meant interference. The motion meant instability in measurement. The crowded field meant confusion. It is a humbling kind of failure, the kind that teaches you that nature does not care about your convenience. The universe did not arrange Alpha Centauri to be easy to study. It simply exists as it is, and if our instruments cannot handle that reality, the fault lies not with the stars but with our assumptions about how observation should work. So the question shifted. If traditional planet hunting methods failed here, if every technique designed for distant, well-behaved stars collapsed under the intensity of our nearest neighbour, what kind of telescope would be needed to break this stalemate? What tool could possibly manage the brightness, the complexity, the interference, and still tease out a signal so faint it had eluded detection for 70 years? By now, Alpha Centauri looked less like an inviting neighbour and more like a locked door. And somewhere in the depths of space, floating in the cold darkness far from Earth, there existed a telescope powerful enough to peer back to the beginning of time itself. The question was whether that same telescope, designed for the faintest whispers of ancient light, could somehow be convinced to look at something far too bright, far too close, and far too dangerous for its delicate instruments to survive. The James Webb Space Telescope was designed for a very different mission. It was built to look back in time, toward faint galaxies whose light has been stretched and cooled by the expansion of the universe for over 13 billion years. Its mirrors, its instruments, its detectors, All were tuned to chase ancient, fragile photons at the edge of visibility. In that role, it is unmatched. But that design carries a price. The detectors aboard the James Webb Space Telescope are so sensitive that bright nearby objects are not just difficult, they are dangerous. Pointing it at a star like Alpha Centauri is like using night vision goggles in front of a searchlight. The incoming light can saturate the sensors, and in extreme cases even risk damaging key systems. For a $10 billion observatory with no chance of repair, floating alone in the darkness far from Earth, that is not a risk anyone takes lightly. From the beginning, the rules were clear. Do not point at very bright stars. Do not waste time on nearby systems that threaten the instruments. The telescope was meant for early galaxies, dusty stellar nurseries, and the atmospheres of distant exoplanets around fainter stars. Alpha Centauri simply did not fit into that picture. Most astronomers accepted this. When they looked at the specifications, they saw a finely tuned machine for deep space, not a blunt tool for nearby blinding targets. The phrase "too sensitive" became a quiet verdict. Too sensitive to acquire such a bright star cleanly. Too sensitive to keep its tracking and acquisition systems within safe limits. And yet, that is where curiosity often pushes hardest against the word impossible. If Alpha Centauri is the nearest realistic destination for future interstellar missions, could humanity really afford to ignore the one telescope powerful enough to glimpse cold, mature planets there, just because it was never meant for this job? Somewhere in that tension between strict safety rules and the pull of the closest star system, a small group of scientists began to wonder, what if the James Webb Space Telescope could be persuaded very carefully to look at something it was designed to avoid? There is a moment in every investigation where the rules start to feel negotiable. The evidence refuses to appear, the usual tools fail, and someone quietly asks a dangerous question. What if the limit is not in nature, but in our own caution? That question brought one scientist to the edge of what the telescope was allowed to do. Charles Beechman did not want to use the telescope as it was intended. He wanted to bend it, to aim it very carefully at the blinding heart of Alpha Centauri, and ask it to see something no instrument had ever seen there before. Instead of chasing reflected starlight, his plan was to search for heat. The James Webb Space Telescope carries an instrument called MIRI, the mid-infrared instrument, tuned not to the blue glare of stars, but to the soft glow of warm objects in the dark. Mature planets, especially gas giants, do not shine like stars, but they do emit thermal radiation. In the mid-infrared, a planet can stand out against its star in a very different way. This shift in strategy mattered deeply. Reflected light is like trying to see a dust grain lit by a spotlight. Thermal light is like watching for a tiny coal glowing in the embers. Around a star like Alpha Centauri A, a planet in the habitable zone is cold by stellar standards, yet still warm enough to glow faintly at mid-infrared wavelengths. That glow is what Beechman set out to find. To do this, the team turned to a coronagraph built into the mid-infrared instrument. A coronagraph works by sculpting light, carefully cancelling out the central star so that faint nearby objects can emerge. In this case, they used a design called a 4-quadrant phase mask, which splits the incoming starlight into 4 regions with different phases so that the star largely cancels itself out. It is an artificial eclipse, created not by the moon, but by interference. If it worked, the coronagraph would allow the telescope to detect objects 10,000 times fainter than the star itself, right next to it. On paper, it was exactly the kind of technology needed to reveal a hidden planet. But the brightness of Alpha Centauri pushed this technique beyond anything it had been tested on. The system was never meant to operate at this level of intensity. Failure was not just possible, it was expected. The detectors might saturate, the coronagraph might leak, the data might be unusable. For a mission as valuable as the James Webb Space Telescope, devoting time to such a risky experiment was a bold decision. And yet, this is how boundaries move. By taking a tool built to study the earliest galaxies and forcing it, gently but insistently, to look at the star next door, there is something almost unsettling about asking a machine in deep space to aim at the wrong place on purpose. Not because you are confused, but because that is the only safe way to reach the right place. With Alpha Centauri, that is exactly what had to happen. The telescope could not simply lock onto Alpha Centauri directly. The star was too bright for its sensitive acquisition systems. Staring at it head-on would be like trying to focus a magnifying glass on the sun. The first step of any observation, the act of pointing, had become the main barrier, so the team designed a workaround that felt more like celestial sleight of hand than normal targeting. Instead of telling the telescope to look straight at Alpha Centauri, they instructed it to lock onto a nearby, safer reference star. This anchor star was bright enough to guide on, but not bright enough to threaten the detectors or blind the tracking cameras. From there, the telescope performed a blind offset, sliding its gaze by a precisely calculated angle until Alpha Centauri drifted into the chronograph's field without ever being used as the initial guide. The numbers behind that shift were brutal. The required accuracy lived in milliac seconds, tiny angles so small that if you stood on Earth, they would match the width of a coin seen from thousands of kilometers away. If the offset was even slightly wrong, Alpha Centauri would land in the wrong part of the chronograph, letting starlight leak into the dark zone where planets were supposed to appear. One misstep, and the entire observation would be flooded with glare. It's okay if your mind wanders here through these technical details. The precision is remarkable, but the feeling is what matters. The patience, the delicate choreography of light and distance and timing. If you drift off while imagining that distant machine threading its needle in the darkness, that's perfectly fine. The telescope is patient, and so are we. The stage was set, the choreography was planned, and now came the moment to see whether all this careful preparation would reveal anything at all, or simply confirm what many already suspected, that some targets are forbidden for good reason. There is a particular kind of disappointment that arrives when an ambitious plan meets reality, and reality wins cleanly. Not with a crash, not with drama, just with quiet, undeniable failure. That is what happened when the first observations of Alpha Centauri came back from the James Webb Space Telescope in early 2023. The blind offset worked. The telescope had successfully aimed at the forbidden star without damaging itself. The chronograph activated, the exposures ran, and data began streaming back to Earth. On paper, everything had gone according to plan. But when astronomers opened the images, what they saw was chaos. The chronograph, which was supposed to carve out a dark, clean zone around the star, leaked light everywhere. Instead of a calm shadow where faint planets might appear, the images were swamped with residual starlight. It was like trying to photograph the night sky while someone shines a flashlight directly into your lens. The structure you were looking for gets buried under glare. Then Alpha Centauri b made things worse. Its light, already a known problem in theory, flooded into the field in practice. Scattered reflections bounced through the optical system. Subtle interference patterns appeared where light from the two stars overlapped. The detector was not quietly recording faint signals. It was drowning in bright, structured noise. When the team processed the data, they did not find promising hints or tantalizing patterns. They found unusable images. For those who had warned that this experiment was too risky, the result felt like vindication. A $10 billion observatory pushed beyond its specifications had produced exactly the outcome they predicted. Bright stars behaved like bright stars. Instruments obeyed their limits. The universe had not broken any rules. Alpha Centauri had simply confirmed once again that it was too difficult. Many teams would have stopped there. The telescope had been tested at its edge and found wanting. The data supported walking away. But instead of treating the failure as a verdict, the team treated it as a diagnostic. Every place the coronagraph leaked became a map of where it was weakest. Every artifact from Alpha Centauri b became a clue about how light scattered inside the instrument. They began rebuilding the approach from scratch. New exposure strategies were drafted. New ways of subtracting starlight were explored. Simulations ran to predict what would happen if they changed the observing angle, the timing, the mask orientation. The question shifted from why did this fail to what exact conditions might let it barely work. Failure had turned into information, and beneath the frustration, a quiet possibility emerged. If complete failure could teach this much, what might a near success reveal? August 2024 brought that moment. 3 new observations of Alpha Centauri A were scheduled. Each one demanded hours of patient, uninterrupted staring as the telescope held its gaze on the system. During those long exposures, photons trickled in one by one, slowly building frames that at first glance looked like nothing but chaotic speckles and scattered light. Raw data from around a bright star is never clean. It is messy, full of diffraction artifacts and residual glare that the coronagraph could not fully suppress. But raw data is just the beginning. The real work starts on the ground, where astronomers apply layer after layer of processing to tease signal from noise. They began with reference star subtraction, a technique where images of other stars observed with the same instrument act as templates. Subtract that template away, and sometimes what remains is something real, something unique to your target. On top of that, they used advanced algorithms, methods that do not trust any single frame, but instead look across many images at once, identifying common patterns to remove and rare persistent features to preserve. It is like teaching a computer to listen to a crowded room and subtract all the background chatter, leaving only the one whisper that appears in the same place every time. Out of this careful, exhaustive process, a faint dot emerged, not scattered randomly, not flickering in and out, but sitting in the same location across the processed data. It appeared about 1.5 arcseconds from Alpha Centauri A, a separation that at the star's distance corresponds to roughly 2 astronomical units. That is about twice the gap between Earth and the Sun. Close enough to matter, but far enough to avoid being lost in the star's immediate halo. The team measured how strong the detection was. They calculated a significance of 5.5 sigma, a statistical threshold that in most scientific contexts separates compelling evidence from coincidence. Not absolute proof, not yet, but far beyond the kind of random fluctuation you expect from noise alone. For 70 years, Alpha Centauri had been silent, and now, in the processed glow of mid-infrared light, there was a candidate, a faint point of thermal emission that looked, behaved, and measured like a real planetary body orbiting the closest sun-like star to Earth. They gave it a designation, S1, a placeholder name for what appeared to be a Saturn mass world, a gas giant sitting near the edge of Alpha Centauri A's habitable zone. Its estimated temperature hovered around 225 Kelvin, cold by terrestrial standards, but warm enough to glow faintly in the darkness. If S1 was real, it opened possibilities no one had dared to hope for. Not just a planet, but potentially a world with moons, satellites that might, in theory, harbour conditions for life. Naturally, the team scheduled follow-up observations. Confirmation is the backbone of science. One detection, no matter how statistically significant, is not enough. You observe again, ideally under different conditions, to see if the signal persists. So in February 2025, the telescope turned back toward Alpha Centauri A, aimed at the same region, and began collecting data. S1 was not there. The team processed the images carefully, applying the same techniques that had revealed the object months earlier. They checked and rechecked the coordinates, the offsets, the exposure settings. Everything matched. The only thing missing was the planet. Where a faint thermal glow had appeared in August, there was now nothing but the familiar noise of scattered starlight. They tried again in April 2025. Perhaps February had been unlucky, a brief window where conditions conspired against detection. But April brought the same result. No signal, no dot, no Cern. The planet had seemingly vanished. This was not how planets behave. Planets orbit stars in predictable patterns. They do not flicker in and out of existence. They do not appear for one observation and disappear for the next without explanation. Either as one had never been real, or something deeply unexpected was happening. And somewhere in that space between data and interpretation, between what was seen and what might actually exist, the real mystery began. It's all right if you feel uncertain here, adrift in the same puzzle the astronomers faced. Mysteries do not always resolve quickly. Sometimes they ask us to wait, to sit with not knowing, to trust that answers arrive in their own time. The stars have patience. And so, perhaps, should we? When something disappears that should not be able to disappear, science enters a particular kind of crisis. Not the dramatic kind where theories collapse, but the quiet kind where every assumption must be placed back on the table and examined carefully. Sohan had vanished. The question was why. 3 explanations emerged, each with its own implications. The first was the simplest and least satisfying. S1 was never real. It was a statistical fluke, a random alignment of noise that happened to look like a planet in August 2024, but dissolved under further observation. This kind of false positive is rare at 5.5 sigma significance, but not impossible. Probability does not forbid unlikely events. It just makes them uncommon. If you search enough data long enough, even highly improbable patterns will occasionally appear by chance. But dismissing S1 as pure chance felt uncomfortable. 5.5 sigma is not a casual threshold. It is the kind of detection that in most contexts would be treated as compelling evidence. Walking away from it without deeper investigation would mean accepting that the most significant candidate ever found at Alpha Centauri was nothing more than an accident. The second possibility was more subtle. What if S1 was not orbiting Alpha Centauri A at all, but was instead a distant background object that just happened to sit along the same line of sight? A galaxy, a faint star, something far beyond the system but optically aligned with it. This kind of contamination is a constant problem in crowded star fields. But checks against star catalogues came back negative. No background source matched the position and the spectral signature of S1. The specific wavelengths of light it emitted matched what you would expect from a thermal planet, not a distant star or galaxy. That left the third explanation, the one that required rethinking how planets can hide. What if S1 was real, but the coronagraph's sensitivity varied depending on where the planet sat in its orbit? Coronagraphs do not create perfectly uniform darkness. They have regions of high contrast and regions where suppression weakens. If a planet's orbit is eccentric, looping closer and farther from the star over time, it might pass through zones where it becomes visible and other zones where it drops below the detection threshold. Orbital geometry could explain everything. In August, S1 might have been positioned in a favourable part of its orbit, sitting in a region where the coronagraph worked well. By February and April, it could have moved into a blind zone, a part of the orbit where scattered starlight overwhelmed the faint thermal glow. The planet did not vanish. It just moved somewhere the telescope could not see it clearly. Models supported this idea. If S1 follows an eccentric orbit, the disappearance was not only possible, but predictable. And if that was true, it meant something remarkable. S1 might reappear exactly when and where the model said it should. There is a particular kind of waiting in astronomy that feels different from ordinary patience. You're not waiting for something to happen. You're waiting to see if your understanding of the universe is correct. If the models are right, S1 should reappear in August 2026, returning to the same orbital position where it was first detected 2 years earlier. That prediction is not a guess. It is based on calculations of orbital mechanics, geometry, and the known behaviour of the coronagraph. If S1 follows an eccentric orbit as the model suggests, then by late summer of this year, it will move back into a zone where the James Webb Space Telescope can see it clearly. If it appears exactly where and when predicted, the case for its reality becomes overwhelming. Confirmation would not just validate one detection, it would validate an entire method of searching for planets around the brightest, most difficult targets in our sky. And if S1 is confirmed, the implications stretch far beyond one world. This would be the closest directly imaged exoplanet ever found. Not inferred from wobbles in starlight or dips in brightness, but actually seen as a distinct point of thermal emission separated from its star. That alone would rewrite the record books. But there is more. S1 would also be the oldest cold planet ever directly imaged. Most exoplanets we have photographed are young, hot, and still glowing from the heat of their formation. S1 is mature, having existed for billions of years in a stable orbit around a sun-like star. Capturing that kind of world, one that has cooled and settled into a long-term equilibrium, is extraordinarily rare. It would also be the first mature gas giant found near a sun-like star through direct imaging. Most gas giants we know about were discovered indirectly through their gravitational effects, or by blocking starlight as they pass in front of their stars. Seeing one directly, as a faint glow next to Alpha Centauri, would confirm that even the most challenging stellar environments can host worlds we are capable of photographing if we push our instruments far enough. And then there is the binary nature of the system. Alpha Centauri A and B orbit each other, creating a dynamic environment where planet formation is thought to be more difficult. If S1 exists, it proves that binary star systems can host stable, long-lived planets in regions we once considered too chaotic. That changes how we think about where planets can form and survive. But perhaps the deepest implication is the simplest. If a planet exists at Alpha Centauri, the nearest sun-like star to Earth, it means our stellar neighbourhood is not empty. It means that when we look up at the night sky and wonder what lies beyond, the answer might be closer than we ever imagined. Close enough, perhaps, that future generations might one day send probes there. Close enough that the word neighbour takes on a meaning that stretches beyond metaphor. And so we wait. Not with urgency, not with anxiety, but with the kind of patience that astronomy teaches best. The patience of knowing that the universe moves on timescales far beyond human hurry. The patience of trusting that what is real will reveal itself when the conditions are right. August 2026 is not far away now. The telescope will turn once more toward Alpha Centauri. The data will arrive, the processing will begin, and somewhere in those careful layers of analysis, an answer will emerge. Either S1 will appear exactly where it should, confirming that we have finally learned to see what was always there, or it will remain absent, and the mystery will deepen further, asking new questions we have not yet learned to ask. Either way, the search continues. Because that is what we do. We look, we wait, we wonder. And occasionally, if we are very careful and very patient, the universe shows us something we have never seen before. The stars are still there tonight, steady and patient in the darkness. Alpha Centauri shines among them, holding whatever secrets it holds. And whether S1 is real or not, whether it reappears or fades into the category of beautiful mistakes, the effort to see it has already changed us. We learned to teach a telescope to disobey. We learned that proximity can hide as well as reveal. We learned that sometimes the closest mysteries are the hardest to solve, and if you have drifted off somewhere during this story, that is exactly as it should be. The universe does not require your attention to continue existing. The search does not pause when you close your eyes. Morning will come, the stars will still be there, and the quiet work of learning to see will continue, one careful observation at a time, until the darkness finally yields its secrets, or teaches us new ways to ask.